All right, good afternoon, everyone. If you can hear me, please click on the little green check. All right, good job. All right, welcome to the Center for Disaster Research and Education's final virtual seminar of the fall semester. With us today, we have Steve Goldstein. Steve has 20 years of experience providing weather forecast and decision support at 6 National Weather Service offices in the U.S. Some of Steve's stopping off points have been Washington, D.C. area, Sacramento, California, Reno, Nevada, San Diego, California, and Rochester, Buffalo, New York area. Steve currently is working as one of the new emergency response meteorologists at the Baltimore, Washington Forecast Office. Steve provides decision support to emergency managers, incident commanders, state and county officials, internal government officials, and first responders within the Capital Beltway region. Steve has an MS degree in atmospheric sciences from Texas Tech University and a BS in physics from Clarkson University in upstate New York. He's worked as a weekend TV weatherman for the NBC affiliate in Amarillo. He also works for private weather companies in Texas and Colorado before joining the National Weather Service in 1992. Steve's also a member of the American Meteorological Society and Toastmasters. He's an avid mountain climber and outdoor enthusiast. Before I hand it off to Steve, I'll just say one thing, that all of you are signed in as moderators, which means you can unfortunately do things to the slides. Please try not to use your moderator rights, and we'll let Steve give us what will be a very informative and very educational session for those of us emergency management. Steve, it's up to you. Thank you.
All right, thank you so much. Appreciate everybody dialing in this afternoon. A quick public service announcement for anybody that's planning travel over the weekend, especially out towards State College, central, northern, and western Pennsylvania. There's a very good chance of a significant ice storm starting Sunday morning and continuing through Monday morning. So I would urge everybody to watch the forecasts pretty carefully. Everybody has, I'm sure, heard of what's happened out in Texas and the Central Plains, and as they get some snow today from the front that's moving through, the cold air that stays in place there is likely to contribute to a fairly significant icing event beginning Sunday morning and lasting through Monday morning. So adjust your travel plans accordingly if anybody's planning on heading out that way for the weekend. Anyway, I thank you for the introduction. My name is Steve. I've been with the National Weather Service now for 20 years. And I'm going to talk to you about the new pilot project program that the Weather Service implemented in the beginning of 2012. I'll show you some examples of the incident meteorology program and how it's evolved over the last 10 to 15 years and how it sort of led to these pilot projects. We'll talk about incidents, different types of severe weather, how we plan for them, how we staff for them, and how we provide services for them. We'll also touch a little bit on where the weather enterprise is going. You know, what is the future of weather forecasting? What is the future of decision support services as far as weather is concerned? And we'll then follow up with the opportunity to ask questions. And I'll apologize if you hear beeping in the background. It's actually a fairly active day here at the weather office in Sterling, as we just issued some winter storm warnings for that ice event, even in our western mountains. So hopefully everybody can see a slide that says Building a Weather-Ready Nation, the Next Generation of Weather Service, the Next Generation National Weather Service. That is me. I assure you I am not into setting fires. That is a prescribed burn in Monterey County, California in 2008. And what they did was they brought meteorologists that have training in fires, myself in this particular example, to this prescribed burn to do weather support for this incident. And it gets into the question of what is an incident. So again, just highlighting where we're going to go, we're going to talk about the National Weather Service Incident Meteorologist Program. We'll talk about how we've sort of expanded from fire to all hazards, hurricanes, tornadoes, tsunamis, even earthquakes, and an all-hazards approach to preparedness that the National Weather Service is trying to spread throughout the emergency response community. We'll talk about the Weather Ready Nation Initiative, the National Weather Service pilot project offices and programs, and the Emergency Response Specialist position, which is what I hold. And we'll talk about the future of the weather enterprise. So the Incident Meteorologist program, the first thing we have to ask ourselves is, what exactly is an incident? Well, an incident is defined as an event or an occurrence. It is something that's not planned. It disrupts the state of the system. It disrupts services. It is a defined occurrence that requires some kind of action. And the particular case of the National Weather Service, fire is a good example, wildland fires. Why might fire emergency responders need different types of forecast information than the general public? Well, fires tend to occur in complex terrain. The fire managers need humidity forecasts, the height of mixing layers or mixing height forecasts. They need inversion forecasts and stability forecasts. They need winds on specific areas. This is a GIS map of a fire that was occurring in Idaho. And they need to know the forecast in this particular red area. They need specific information as far as planning where to respond to and how to best fight the fire. They need wind forecasts in specific areas. They need national fire danger rating system forecasts. They need a lot of specialized information. And so for a long time now, the National Weather Service has supported wildland fires. The Incident Meteorologist program was actually developed as long ago as 1916. And what we did was we trained meteorologists to be able to go directly to a fire, an oil spill, or other incidents that require specific types of forecast information. Anywhere where rescue crews are deployed, we will take the area forecast and narrow it down to the place where the incident is occurring, incorporating meso and microscale forecasts. In other words, if you take a look at your National Weather Service forecast and you see a high temperature at an airport like Dulles International or Scranton International, if there's a fire that's occurring in a specific remote area, the forest fires, the planners need forecasts where that fire is occurring. They don't really care what's happening at the airport or at the population centers. They're going to need forecast information for where the incident is. So for a long amount of time, the Weather Service has recognized that we need specific forecast information on site where these incidents are occurring. And what they started to do was any fire that grows large enough to require the deployment of a Type 1 or Type 2 incident management team now comes with its own National Weather Service meteorologist. And we get to the incident, the fire, and we talk directly with incident commanders, and we use the information to help them make decisions on how they are going to respond to the incident based on the weather that's occurring. In other words, if you take a look at this map, and we'll go back to this perimeter here, if they're deciding whether or not to deploy, say, 200 or 300 firefighters on the top of this ridge, they're going to need to know what the winds are doing on top of that ridge. Is it going to be as windy as it was the day before? Is it going to be as stable? Is it going to be as conducive to the possibility that fires will grow or move in a different direction? And of course, we've all heard stories where weather forecasts have gone awry, wind shifts have happened, and firefighters have been killed, sadly, in action. But the incident meteorologist sits side by side with the fire behavior analyst to determine where to best deploy those resources to help stop the spread of a wildland firefighter. So that's what an incident meteorologist does. But incident meteorologists have not just been deployed to fires. They've also been to disasters like the Space Shuttle Columbia. Everybody might remember when that exploded. There was a recovery period where debris needed to be recovered. And they sent an incident meteorologist to that command center to help forecast what the winds were going to do, whether it was going to rain or not, and how weather was going to impact recovery operations, if that makes sense. We've been deployed to the Democratic and Republican National Conventions, the inauguration, for example, in 2013. oil spills, tornado recovery, any particular incident or event or unscheduled occurrence where operations were disrupted and recovery procedures had to be employed. So this is something the National Weather Service has been involved in for a long time. You wonder how many incident meteorologists the National Weather Service has. The National Weather Service is an organization that has about 4,000 people, but there are only 77 incident meteorologists across the country, with about 20 additional people that are currently being trained. We are primarily trained for fire, but we're also trained to do all types of hazards. And what we are conditioned to do is be on a scene within 24 hours. We try to do even better. If we hear that there's an explosion or a hazmat incident or something that requires our deployment, our goal is to be there within 10 hours of incident occurrence. And between the time that we're called and the time that we get there, what they do is they will go to the relevant weather forecast office where the incident occurred. In other words, if there was some sort of chemical explosion in the San Francisco Bay Area and an incident meteorologist was called to go out there, in the 10 hours it takes us to get there, they will go to the San Francisco weather office to get their weather information until the incident meteorologist actually arrives. And the incident meteorologist program received a big boost of enthusiasm after the Yellowstone fires of 1988. In 1988, this was a particular year where more than 80% of our nation's resources were deployed fighting the fires in Yellowstone National Park. There was a tremendous amount of damage that particular year, and it's interesting because I was actually out there that year, and I saw just how much damage had occurred. Before 1988, there were maybe 30 to 40 incident meteorologists. After that year, the number doubled to the current level of 80, which is in place right now. Incident meteorologists are really important to try to ensure the safety of emergency responders. If there's a fire going on in Southern California and we have a gust front moving towards the area, the incident meteorologist has a better opportunity to predict what is going to happen in the near future that might help or hinder recovery efforts. And that's the best reason to have an IMET on site, directly on the scene, to work directly with the emergency responders. The National Weather Service in Southern California might have to forecast for the entire area, but an incident meteorologist will only do the weather for exactly where the incident is occurring. Because they have the opportunity to get a better idea of local conditions and local variability in weather, this is why they realized that the incident meteorologist program was such a boost to national on-site disaster occurrences. And an example of this is the Schultz Fire in Arizona, which is a fire that I was deployed to back in 2010. This is a picture that I took almost the moment I got there. And what I saw, of course, was a huge fire going on the opposite side of this ridge and a giant smoke plume. And in northern Arizona, if anybody's ever been out there, the humidity can be as low as 4 or 5%. It's an area that's very prone to and conducive to wildland fire growth. These are the San Francisco mountains, and they do tend to burn. And after they burn, the debris is prone to areas of flooding and flash flooding when winter rains occur. So the Schultz Fire is something that I was deployed to in 2010, and this is what the incident commander is showing where the fire is occurring. So the GIS people are very important to giving us maps of where the fire perimeter is, and also at night they will fly reconnaissance aircraft and helicopters over the fire to determine whether it's growing, staying the same, or shrinking in size. That way, when the firefighters deploy at 0600 in the morning, the National Weather Service meteorologist briefs upon the weather conditions, and then they make the decision where to send the firefighters. If you look at this map, you see Division V, Division B, Division B, Division Y. If the fire is moving from south to north, they might decide whether or not to deploy a lot of firefighters on this Division V. But that decision may be entirely dependent upon the amount of wind they're expecting, the humidity they're expecting, or the number of thunderstorms that could occur on that particular day. And you see that what they're going to need is a forecast for this area in pink. This is the Flagstaff, Arizona forecast area, and Flagstaff is over here, about 10 miles to the south and east. But they don't care what the weather's doing in Flagstaff itself. They don't care what the temperature is or how much cloud there is. They want to know how much wind is going to blow and from what direction and when it's going to fire up. They want to know if there's going to be any thunderstorms or any erratic winds that might occur that could change the direction that this fire goes. And in this particular incident, I remember that this black area here was an area that they were deploying a lot of the firefighters. They were trying to keep the fire from spreading from the south and east over to the north and west where some other population centers were occurring. And so we concentrated on this Division V. What were the winds going to do? So how do you get the forecast for that particular location? Well, one thing that we can do is we can order automated 24/7 weather sensors to be positioned right on this ridge top. Once the incident meteorologist is in place, we will look at the topography, we'll work with the Forest Service and the fire behavior analyst, and we will decide where the critical places are to deploy weather monitoring equipment. And we'll get into that in just a moment or two. And once we have those sites deployed, we can then monitor the conditions 24/7 if we get them teleconnected to our computers. You can't make a weather forecast unless you know what is going on at the present time. So we have to, as quickly as possible, get those sensors deployed so we can then begin to forecast trends in temperature and humidity and pressure, if that makes sense. And again, these are highly specialized forecasts. And that's why you need a meteorologist directly on site at a fire like this. At this time, back in the summer of 2010, this was the only fire that was going on across most of the entire United States. So fortunately, they were able to deploy a large amount of resources directly to this fire, which helped this incident become from getting too much worse. This is a picture that evening. You'll notice that at night, as the winds begin to sink and high pressure sets in, you get this sort of stable smoke layer at the top of the mountain. So it becomes more stable at night, more unstable during the day when the sun heats the mountains and the air begins to rise. When that is going to occur and what the winds are going to do when that happens is one of the main responsibilities of a fire weather forecaster. And we have to be trained in recognizing diurnal wind patterns, up canyon and down canyon wind patterns, and what particular wind is going to be dominating the wind regime at that time. And the fire environment, if you look at what drives the behavior of fires, what is the most variable component of the fire environment? Is it the fuels? Is it the trees that are burning? No, that pretty much stays the same. Is it the topography? No, that stays the same. Is it the weather? Yes, the weather is the most variable component of the fire environment, and that's why you need a meteorologist on site at a fire to help predict what those winds and humidities are going to do. If you take a look at this particular picture, would anybody think that this is an active fire behavior day or a not active fire behavior day? And the answer is this is not an active day, and the reason is because the fire is clinging to the ground. It's just burning the ground fuels. It's not getting up into the trees and burning the tops of the trees. So if I look at a picture like this, and if I get on site and get onto the fire line and see that the fire is creeping along the ground and not making it up into the tops of the trees, I will infer that the atmosphere is fairly stable and that there isn't a high risk of extreme fire behavior. But what if you see something like this? This is a day where the fire gets into the tops of the trees, crowning and torching is occurring. You're getting huge 30, 40-foot flames that are bursting off the tops of the trees. This is obviously an active fire behavior day. And just visibly seeing this lets me know that the fire is truly in an explosive environment. And what I'll try to do is get a hold of the weather conditions, find out what the humidity is, find out what direction the wind is blowing from and blowing to, and how that is going to change over the next, say, 12 to 14 hours. This particular day is an active fire behavior day. These clouds are just being caused by smoke particles that are being lifted into the upper atmosphere and condensing. They almost look like thunderstorms, but what they are smoke clouds that are being caused by the fire burning actively. You can see there's some sort of prevailing wind that is lifting the tops of these clouds high up into the atmosphere. You see the sharp definition of the tops of the clouds. That is an indicator of unstable conditions. And that's very important for firefighters to know if there's a fire that's going on upstream or downstream of this particular event. Again, just more visual clues on stable and unstable conditions and conditions that are conducive to rapid fire growth. What are the most important weather elements to fire behavior? Wind is the most important. Wind will influence the spread of a fire, how fast it spreads, the direction that it spreads. Wind forecasts are the most important thing that an incident meteorologist provides to a fire behavior analyst. Humidity is also important, though not as variable. Fuel moisture is important. If you think about the Sierra Nevada, or if you think about the mountains in northern Arizona, during the winter time, it's not uncommon for them to get 80 to 100 mile an hour wind gusts, but during the winter, those mountains are covered by a lot of snow, so the fire danger isn't as high. During the summertime, those trees are dry. There's no snow. The fuels, the components that burn have had the opportunity to dry out. And how do we measure that? They actually take pieces of the tree, they burn it, they calculate how long it takes to completely dry out, and they mathematically come up with something called fuel moisture. When this fuel moisture goes below 10%, that is an indication that fire conditions are extremely volatile. Therefore, if the fuel moisture is low enough and the winds are strong enough and it's dry enough, fire weather forecasters will issue something called a red flag warning. The red flag warning doesn't mean that we're forecasting fires to occur. It means that conditions are such that if a fire starts, the meteorology is conducive for the rapid spread of a wildland fire. And that's what a red flag warning means. I hope everybody understands that, because those are issued all across the lower 48. They're issued for Pennsylvania, Virginia, and Maryland. Red flag warning doesn't mean we're expecting fires. It means that if a fire starts, it has the potential to grow quickly, get out of control, and need more than just initial attack resources to be suppressed. So I hope everybody understands that. The fire forecaster looks at stability, cloud cover, temperature, and pressure. These are not the types of things that you see when you watch the news at night and try to hear what the weather is going to do. The TV meteorologist at night will tell you what the temperature is going to be, whether it's going to rain, how it's going to impact your life, how the weather is going to be. But I'm trying to demonstrate that a wildland firefighter manager needs specialized information to help them determine how to best fight the fire. And I hope I've managed to do that in the last few slides. And again, to know how a fire is going to behave, to forecast the weather, you absolutely positively have to know what the weather is doing now. You can't forecast the high temperature tomorrow unless you know what the high temperature was today. On the left, this is the ASOS, the Automated System Observing Station. These are on site at most major airports across the lower 48, from Philadelphia to Scranton to Washington, D.C. They are automated units that continuously monitor temperature, pressure, visibility, precipitation, humidity, and all other meteorological elements. The advantage to them being automated is that they are able to continuously monitor conditions 24/7. The disadvantage is you don't necessarily have somebody walking outside looking around the sky and taking an augmented observation. As an example, if you see this device that's located right here, it actually emits a laser beam of light from the left side to the right side. If that laser beam begins to become less strong, the unit is figuring that that is because there are clouds, weather, or something obstructing the visibility. That's important information. There's a temperature sensor, a wind sensor on top, a precipitation gauge, and all sorts of other automated information. This was developed during the modernization of the National Weather Service during the mid-1990s. These were deployed at every airport and a lot of other military sites across not only the lower 48, but Canada, Mexico, South America as well. So we have an extensive network of automated weather information. But what if you are deployed to a fire that's in the middle of the George Washington National Forest, or somewhere in the Boise National Forest where you're not close to any population center? Well, what you get is these remote automated weather observing sensors. And this is what it looks like, this diagram on the right. The moment the incident meteorologist arrives, he has the ability to order up to a half dozen of these automated weather monitoring systems. And it comes with a wind meter, a humidity meter, a temperature meter, a sky sensor, all types of weather monitoring information. Because again, you have to know what the weather is doing in the valley, on the ridge, and in the mid-levels of a fire to fully understand how the fire is going to behave. How is the weather going to change? So what you're looking at on the right-hand side is called the Remote Automated Weather System, or RAWS. Once we get there, we confer with the Forest Service official and order maybe 3, 4, 5, 6 of these. Technicians are deployed from the National Cache in Boise, Idaho. With these sensors, they deploy them where we tell them to deploy them. And then they begin transmitting data to us as soon as possible, and we can begin to get a handle on what the winds are doing in the valley, on the tops of the ridge, and in remote areas of the fire. I cannot emphasize how important this is in the forecast process. Without this real-time weather information, we would not be able to forecast what conditions are going to do in the next 24 to 36 hours. So people may not know that we have the ability to order these sensors, that there's a national cache of them established in Boise, Idaho, that we order them, that technicians are dispatched to a fire, and that we have the ability to deploy these within a 12 to 36 hour period as required by national directives. A lot of national forests have towers that are set up that are actually staffed 24/7 with weather observers. The weather observer simply climbs the tower and lives in this little box for a 6 to 8 hour period. What they can do is look out across the entire forest and physically see what is happening with the fire behavior. They are activated when the fire preparation level reaches an extreme level. These tower observers are very, very important to National Weather Service and fire behavior forecast officials. There is simply no substitute, despite the incredible amount of computer technology that we have today, to physically looking out the window and seeing what a fire is doing. The fire meteorologist is equipped with a belt weather observation kit. If he is certified to do so, he will actually walk out onto the fire line and spin the weather and record it every hour to 2 hours. On the right, you see what these remote automated systems look like. They come in a case about this size. The technicians unpack them and set them up wherever we need them to. And then we augment that information with a physical taking of weather every hour if we can. And in this belt weather kit, we will see a temperature, humidity thermometer, and you spin the thermometer to see what the humidity is doing to get a dry bulb and wet bulb temperature. And then we have a chart where we compute humidity. We have a handheld anemometer in here. We have slide rules, compasses, and this is exactly what field work looks like for an on-site incident meteorologist. Again, you need somebody who is physically capable to take all this equipment into the backcountry and generate weather observations where the fire is occurring as often as possible. So an incident meteorologist has to go through specialized training to be certified to be deployed on the fire, and they actually become a part of the firefighting team. If you look at this picture on the right, you'll see this gentleman is wearing a Nomax top and pants. These are flame-resistant pants in the unlikely event that they get caught in the fire. There has never been an occurrence where a meteorologist has been put in harm's way because of a wildfire. But there have been situations where the meteorologist has had to shelter in place because the fire has changed direction rapidly. Because of that, we are required to be certified in the use of fire shelters. We are required to be certified with aviation and helicopter safety. We are required to be certified in firefighting techniques and the incident command system. So again, the 77 of us that are certified to do this stuff go through an extra level of training to be of use to firefighters and firefighter officials when fires break out. And this belt weather kit, simply walking out and taking observations where you are, there is no substitute for that amount of accuracy regardless of how evolved our computer technology has become, and I can't emphasize that enough. Another thing that they give us is weather balloons. So we take a sensor, we put it on a weather balloon, and we launch it. To understand what the weather is going to do at the surface, you have to have some kind of an idea of what the weather is doing aloft. We can release these whenever we want to, and a computer program will generate plots for us. So this is what an incident meteorologist does. In this particular case, they're at the bottom of a valley. As you can see, the balloon is not particularly large, but we get a tripod. We lock onto it, and our antenna, which is probably located back over here, will lock onto the balloon and plot it as high as it goes until it bursts. And the information that we get back looks something like this. Every minute we will get the elevation of the instrument, the direction, how high it is, the direction of the wind, the speed, and all of this particular weather information is loaded into a computer program. That way we can get extremely valuable weather aloft, winds aloft, temperature, pressure, humidity aloft information as you go up the first 5,000 feet from the ground level. And this is exactly what the plot looks like. So getting this on site at the fire is huge. We don't really care, again, looking at the Schultz fire, what the weather is doing in Flagstaff. We want to know what the weather is doing right where the fire is. And this information gives us an idea of how stable the atmosphere is and what kind of winds might be mixing down to the surface and when. And those decisions then are taken by the fire behavior analyst to help decide where to deploy the firefighters. So I hope everybody understands how valuable having a meteorologist on an incident like this turns out to be. This is a trainee, Mike Smith, that I had at this particular fire. He's reviewing some upper air charts, and this is what they send us with. A printer, a computer, a satellite dish, a cell phone. Normally the fire itself will have a landline, and in this particular way we can go ahead and decide where to deploy firefighters for an incident of this size. Fire camps are usually set at the perimeter of a national forest boundary. The tents is where the incident command sets up. The emergency response vehicles are deployed at incident command. Firefighters themselves will usually be camped out well up into the hills. So after giving a briefing to the firefighters that are going to go up there at 0600, we then usually transition to where the firefighters themselves are deploying from on the side of the hill. The firefighter camp can be as big as 500 to 1,000 people depending upon how big the fire can get. And it can get really crazy because people are going every different direction at once. But having an understanding of the incident command system and how it deploys to an event like this is critical for an incident meteorologist. And this is an example of a briefing that we give at 6 o'clock in the morning. A really big or active fire will have 3 shifts of firefighters 24/7. They'll have a day shift, say from 6 to 2, a swing shift from 2 to around 10 or 11 p.m., and then an overnight shift that deploys from 11 p.m. to 7 a.m. When fires get really, really large, all 3 shifts will require briefings. Additionally, incident commanders, city planners, managers, and the media will need their own briefings. Air ops, helicopters, fixed-wing aircraft will need their own briefings. I have had fires that I've been on, like the Esperanza fire in Southern California, where I've been briefing the air ops people while I've been driving from one meeting to another. It can get absolutely crazy, so you have to make sure that you're communicating information clearly and precisely. And you'll see all these maps in the background, and usually there's some sort of video projection system. They are paying very close attention to what the meteorologist is telling them, because then they're going to plan where to put these firefighters. And I'll tell you, you do feel a lot of pressure. You do not want to give them the wrong information. The information you're giving them needs to be accurate, because you'd hate to give them a wind forecast that doesn't pan out, and they would put firefighters in harm's way. The bottom line is, we all understand there is an inherent uncertainty in the science of forecasting the weather. And we have a lot of computer models that we can look at. But there's no feeling in the world like messing up a wind forecast when 300 firefighters are being put at the top of a ridge. The bottom line is, you do the best that you can with the information that you've been provided to. Sadly, sometimes it doesn't work out. But our computer models are getting better and better with each passing year, and we're doing a better job of protecting those firefighters, the townspeople, and the resources with each passing year that goes by. The pressure is enormous. Home sweet home, this is what it looks like. A lot of times the incident meteorologist camps out with the firefighters at tents that are at the base of the fire. It's not for the faint of heart. You have to enjoy the outdoors. You have to be able to camp out in a tent for up to 16 days at a time. The conditions are harsh. You may begin your day at 4 o'clock in the morning and not end it until 11 o'clock at night. It's very exciting. It's extremely rewarding, because the incident commander is making decisions based directly upon the forecast that you're giving them. But you have to be able to bring a high level of energy and endurance to fires that may last as long as months at a time. Because of union regulations, we are not allowed to be out more than 16 days in a row. We are required to be given 2 full days off after 16 days, and we have to leave the incident. But these fires can be very physically and mentally draining, especially if there's 3 shifts of firefighters that are running concurrently. So the risk is high. The reward to me is very high. Does anybody have any questions so far about anything I've said? All right, as we proceed, this is the Schultz fire in northern Arizona in 2010. This is a forecast that I gave for them, and I'm giving a forecast directly for this fire. I'm indicating what the high temperature is going to be. Look at the minimum relative humidity at 8,500 feet, 6 to 10%, very dry. So obviously wind gusts to 22 miles an hour with a humidity of 10% is going to cause fire to behave fairly erratically. This Haynes index is an index that goes from 1 to 6. 6 is the most active, 1 is the least active. On this particular day, a Haynes index of 6 means that fire will behave actively, erratically, and responsively to meteorological conditions. One of the things I want to point out at this point in my talk is the National Weather Service has realized that instead of issuing forecasts in this text format, there is a value of issuing forecasts in a picture format. So what I did was I developed a graphic that showed why the fire was behaving so erratically. It was an extremely dry period from April through June in southern Arizona, definitely in the 90th percentile as far as dry moisture. Long-term drought definitely encourages active fire behavior. And presenting weather information graphically, as opposed to presenting it text-wise, is one of the big changes that the National Weather Service has undergone in the last 2 to 4 years, and one of the things that us emergency response meteorologists are responsible for in expanding decision support services. So please keep in mind the difference between a forecast that looks like this and a forecast that looks like this, and understand which particular format is able to convey more information in a shorter amount of time. And that's exactly what my job is as an emergency response specialist. So as we get into an all hazards approach, understand that 95% of all presidential declared disasters are weather or flood related. Because of that, the National Weather Service has understood how important it is to integrate into the emergency management community and get an understanding of how they use our products and what they do when they receive weather watches, warnings, and advisories. The weather fatalities graph shows that most people die from heat events. Flood is a close second, with tornado, lightning, and tidal or rip currents being a close third, fourth, or fifth. Heat is one of those silent killers. If anybody remembers the derecho that moved through the mid-Atlantic in 2012, that caused an extensive amount of power outages. After the power went out, a lot of people didn't have air conditioning, and at least 39 people died in the state of Maryland in July and late June alone. That constituted a true weather emergency. Our ability to forecast heat index is something that we've been working on very hard across the country over the last 2 to 5 years. This just shows an average. It is not incident adjusted like Hurricane Katrina or, Tropical Storm Lee, Tropical Storm Allison. There are obviously exceptions to this, but just looking at that graph, your eyes are drawn to heat, your eyes are drawn to hurricanes, and your eyes are drawn to flooding. And of course, tornadoes and lightning also are fairly common as far as causing U.S. weather fatalities. So what we take a look at is that in 2011, there were, I believe, 14 disasters across the United States, each one causing at least $1 billion worth of damage, from snowstorms in the Northeast to Tropical Storm Lee to Hurricane Irene, floods over the Missouri River, drought and fires in Texas. Texas was on fire almost that entire year, and we had incident meteorologists rotating in and out of the state of Texas for the entire year that year. Floods over the Mississippi River and the Midwest. The tornado outbreaks down in Alabama and Tuscaloosa. Everybody saw the YouTube videos for those. $9 billion worth of damage and 321 deaths on that year alone. And the blizzard, the Groundhog Day blizzard that happened up in the upper Midwest. So after 2011, the National Weather Service took a look at this map and said, maybe we need to take a harder look at how emergency managers use the warnings and watches that we issue. Maybe we need to change the way in which we present our information. And what the director of the Weather Service did that year, his name was Jack Hayes, is he picked 6 separate sites, one in Washington, D.C., one in Tampa, Florida, Virginia, one in Southern Region Headquarters in Dallas, Texas. There was another one actually in Bismarck, North Dakota, of all places. They were going to do the western United States, but they ran out of funding. And what they did was that at those 6 locations, they hired 3 additional full-time incident meteorologists at those 6 offices. They wanted meteorologists that had experience deploying to incidents, whether those incidents be fire, flood, oil spills, tornado outbreaks, what have you. Each of those incident meteorologists was brought to those 6 field offices in January of 2012. And it became our job to query the emergency managers and emergency responders on how the National Weather Service issues its products, how we can improve, and how we can better the relationship and the partnership between the National Weather Service and emergency managers. In other words, we wanted to go from a point where the emergency manager was a customer or user of our products to the point where the emergency manager was a true partner. In other words, that the two of us would collaborate about the weather incident that was about to occur, and we would help them make decisions in how weather was going to impact their particular area of concern, if that makes sense. And this whole thing is called the Pilot Project Weather Ready Nation Initiative. And that's what I am a part of, along with incident meteorologists in Tampa, Florida, Dallas, Texas, Charleston, West Virginia, Bismarck, North Carolina, and National Weather Service headquarters in Silver Spring, Maryland. So I can't emphasize strongly enough how 2011 and all the disasters that occurred that particular year play a role in the direction that the National Weather Service is going to head over the next 5, 10, and 15 years. Understand that the National Weather Service modernized technology back in the mid-1990s when we deployed the Doppler 88D weather radars. Those radars gave us the ability to interrogate the structures of storms and give us increased warning time for tornadoes. That particular time, we increased the warnings of tornadoes, the lead time, from about 7 minutes to 18 minutes. Doesn't sound like much, does it? But figure that if you've got 18 minutes to prepare for a tornado, that's huge. An extra 5, 10, 15, 20 minutes means everything. And these dots, where you see these dots, is where these specialized radars were set up to occur. So for you folks up in Millersville, there's a weather office in Mount Holly, there's a weather office in State College, there's a weather office in Sterling, Virginia. And we determined where those were going to be based on how far those new weather radars were going to be able to see. And we have an ability to give people sometimes up to a half hour. Everybody might remember the horrible tornadoes that occurred in Moore, Oklahoma this year. We actually gave 44 minutes of lead time in the tornado warnings for those particular tornadoes. Granted, it's hard to protect yourself from 200-mile-an-hour winds, but every time we can give an extra minute, an extra 5 minutes to a tornado occurring, we give ourselves more time to protect the citizens and give them more opportunity to take precautive actions that they can take to protect their lives, of their loved ones, and of the community. So this Weather Ready Nation initiative that we're going through right now is the second big modernization that the National Weather Service has gone through in the last 20 years. And I can't emphasize how significant that is, and we'll talk more about that in the slides that occur. So the next generation National Weather Service is focused on on-site decision support. In the upper left, you'll see a picture of me doing the weather for the Grand Prix and G8 presidential summits up in northern Maryland. This is the command center, and this is me giving them up-to-date weather information. On the upper right, these are some of the new graphics that we're producing. We've got most likely event, the best case and worst case, if you will, scenarios. We're trying to indicate a range of possibilities in our forecasts. On the bottom left, that's Ken Wadolski. He's our Maryland representative doing a weather briefing. The bottom right is a picture from the Maryland Emergency Management Agency in Reisterstown, Maryland during Hurricane Sandy. It's difficult to see in this picture, but up front is the governor of the state of Maryland with his entourage standing up there. I'm actually standing right next to him, and from sitting in these desks and at these chairs are people from Public Works, Education, different communities. They need specific weather information to know how the hurricane was going to impact them. The on-site meteorologist gives that information so they can take precautionary actions to help better protect themselves. These are some of the highlights of what the Weather Service is going to get into over the next 5 to 10 years. It's the next generation of National Weather Service. It is not just issuing forecasts, but providing either on-site support, video conferencing, WebEx meetings, conference calls, and specialized emails to particular customers. This pyramid of support that we've developed here in Sterling goes kind of from a widespread, broad situation to a high impact situation like Hurricane Sandy or the presidential inauguration that we had back in January of 2013. If a meteorologist can be actually on site to an incident that is going to impact 500,000 or 1 million people, there is simply no better way to make sure that weather information is incorporated into decision-making processes. This pyramid of support is what all of those 6 offices are developing, so please understand that we've worked hard to develop that. So we're going to go through this pyramid real quick from lowest to highest. The first level of decision support is a heads-up email. We issue these if we think there is a 30% chance that a weather event is going to exceed warning or advisory criteria 7 days out. We will send emails to all of the emergency managers in the counties in our warning area. They will get this heads-up email, and at least they will be clued into the fact that there's something that they should pay attention to. That's the first level. Once we start those, we issue them once a day until either a warning or watch is issued or until the threat has been mitigated. The next level up is conference calls, best worst slides. In this particular slide, you're looking at a snow event. So what we're going to do is we're going to put out a slide that shows the worst case forecast, the best case forecast, and the most likely forecast. So we're going to incorporate uncertainty in computer models into our forecast. We will say, look, we're forecasting 2 to 4 inches of snow, but we've got some models that are showing as much as a foot of snow, and we'll put that in our worst case slide. Best case slide, we're saying we've got some models that are only showing an inch or two. That way it will give the emergency manager a range of possibilities. We'll issue these for tropical systems if we're in the National Hurricane Center's cone forecast, if flash flooding is anticipated, if we're expecting more than 6 inches of snow or a 1/4 inch of ice, or some sort of widespread or regional severe weather or tornado outbreak. We started issuing these graphics last year. They have been very popular and very much appreciated by our emergency responders. So here's just a closer look at what that slide looks like. And another thing, if you look in the top right, we will show what time the impact is expected to begin. Looking at that graphic, it's a little hard to see, but you see 1200, 1300, 1400, all the way up to 1800. This way across the Sterling, Virginia County warning area, what we're showing is that the incident will occur somewhere between noon in the west and 6 p.m. in the east. And what does an emergency manager want to know? How bad is it going to be? How long is it going to last? What's going to happen? And what is your confidence level? And in one graphic, we're producing those slides to show the emergency manager what to expect. This is all brand new stuff. We just started this last year, but you're going to see every National Weather Service office across the country begin to issue these starting this winter. We're issuing best case and worst case scenarios. Here's a case from a storm in March of 2013. Last year we had 4 storms in the Middle Atlantic. We're saying the worst case is 10 inches of snow across the Beltway, Washington, D.C., Baltimore metro areas. Best case, if you will, only 2 inches of snow. Did you know that that rain-snow line, if it varies by 40 miles across the metro areas of Baltimore and Washington, D.C., it impacts 7 million people? To get a forecast accurate as far as the rain-snow line within 40 miles, 3 to 5 days out, is truly a challenge. Our computer models are getting better and better, but that's some pretty darn good forecasting that you have to be able to do. So what we've decided to do is to issue a range of possibilities. There could be as little as 2 inches of snow if it's more rain, or there could be as much as 10 inches of snow if it turns out to be snow. This best case, worst case, or range of possibilities, setting the goalposts, if you will, from a weather event, has been very popular with the emergency managers, because what are they going to do? They're going to take a look at this worst case scenario, and they're going to decide if they need to staff or plan for this worst case scenario. What an emergency manager, of course, looks for is the highest level of acceptable risk to take on by mobilizing resources. We can communicate that to them by looking at ensemble or average forecasts and issuing that to them as often as updates warrant. Other things we have: current snow accumulation forecasts and our confidence level in our forecast. In this incident, we were highly confident that there was going to be a lot of snow in the western mountains, but our confidence decreased as we got towards I-95. That's fairly typical. The rain-snow line tends to be right along I-95, and that's where all of the population is. But we let people know that we're moderately confident that this event will be rain south and east of the Beltway, that the rain-snow line will be somewhere along the Beltway, and that we're more confident that it's going to be all snow west of the Beltway. What emergency managers have told us is they want to get inside the head of the forecaster and understand why they're forecasting what they are. The deterministic forecast will always be available. That's this graphic on the left. It's showing 1 to 2 inches of snow or less than an inch in the coastal plains, maybe 4 to 6 inches along the I-95 corridor, and upwards of 1 to 1.5 feet of snow west of the Blue Ridge. That's also very important forecast information. That will always be available. We have a timing graphic where we're showing when the event is going to occur, and we have our watch warning graphic in the right-hand side, which shows that we have a winter storm warning in this case for almost all areas of our county warning area except for the immediate coastal boundaries. So if you folks are looking at the Mount Holly Weather Office, or if you're looking at the State College Weather Office, this is the kind of stuff you are going to start seeing over the course of the next winter, and I'm sure that they will be advertising that as well. And this winter we're also going with probabilistic forecasts. We're going with the chance of seeing an inch of snow, the chance of seeing 2 inches of snow. In this case, we're pretty confident that there'll be an inch of snow along the I-95 corridor. The most likely forecast here is 4 to 8 inches of snow, but we're showing that there's some forecasts that are going as high as 8 to 12 inches. An emergency manager needs to know that. They need to know that there's a chance that there could be as much as a foot of snow instead of just 4 to 8 inches, and they have told us they want to know that. As we go up to the higher levels in the pyramid, video conferencing capability. If the National Weather Service contacts emergency managers and says we want to have a video conference, that is going to get their attention. They're going to say, wow, that's pretty significant. They must want to tell us something substantial. So we have the ability to now have video conferences with our emergency managers. And the highest level, of course, is on-site support. This is Hurricane Sandy, but things like the July 4th fireworks in the D.C. area, the inauguration, the G8 summit, the Grand Prix race in Baltimore, the incident may not be weather related. It might just be a large gathering of people, but it might be something that's highly dependent upon the weather. If we have these and we get the request from the emergency managers, we can support them with a meteorologist that will go directly to the command center and provide them with site-specific forecasts. And your area will have that as well. We do tabletop exercises because training is really important. As we get into the summer, we will train to be prepared for hurricanes. As we get into the fall, we will be trained to be prepared for winter storms. And that's what we've done with our emergency managers in our area. To give you an idea of how impact-based decision forecasting differs from the types of forecasts you have seen, an impact-based forecast will look something like this. 3 to 8 inches of snow, but we might tell people you're going to get 2 inches an hour with a temperature between 32 and 36 degrees. That will definitely result in gridlock of traffic during the rush hour. That is an impact-based decision support forecast, and you can see how it differs from the traditional forecast. This afternoon, for a flood example, 5 to 10 inches of rain, flash flood warnings in effect. But what we'll tell them is these flood-prone areas are going to be inundated with water between, say, 5 p.m. today and 5 p.m. tomorrow. So comparing the forecast on the left to the forecast on the right shows you where the National Weather Service is going. A traditional forecast would say something like a 60% chance of thunderstorms in the afternoon. The impact-based forecast will say thunderstorms between 2 and 4 p.m., which could cause 30 to 60-minute flight delays. That might be the kind of forecast we would give to Dulles Airport, D.C. National, or Baltimore Washington International Airport, or Philadelphia International Airport. Look at the graphic on the left. Heavy snow with 8 to 12 inches. On the right, roads will become packed with snow and ice after 2 p.m. How do we determine what is going into this impact-based decision support? We are meeting with every emergency manager who is responsible for protecting the public. They will give us their impact, we'll match them with our forecast, and this is the kind of stuff we're going to be issuing over the next year or two. The National Weather Service is gearing heavily towards the impact from weather, not just the weather that is going to occur. So please understand, it's a big paradigm shift. We meet with emergency managers, we categorize winter storm impacts, severe weather impacts, flash flood impacts, heat impacts. We put it into a database, and when the National Weather Service forecaster forecasts certain conditions, the impact is spit out and we put it into our watch and warning text. Understand this is a really new way of doing things, and so far it's been met with a lot of approval across the area. We're also doing a lot with mobile technology. INWS, emergency managers, can subscribe to this service. They will get a polygon if their area is under a direct threat of particular types of weather, whether it be tornadoes, hurricanes, ice storms, flash floods, what have you. If the polygon encompasses their area, they'll get a text alert on their smartphone, and they can distribute that to all of the people who are responsible for caring for vulnerable populations. This is a big change, and they'll get a text that looks like this: flash flood warning in effect for your area until 1:15 in the morning. Avoid flooded areas. Check with the local media. Understand that there's a difference between iPause and the wireless alerts that you receive from Sprint, Verizon, and AT&T. Those are things that you will receive automatically unless you opt out from those. But they are helpful. We understand that if a tornado warning is issued for a certain area of a county, every area in that county is going to get a text alert. But we would rather have you keyed into the fact that dangerous weather is occurring somewhere in your area rather than worrying about the false alarm rates. This is really good at targeting the general public, because no matter where you live, if you have a smartphone, you're going to get that alert from the wireless companies like Verizon, Sprint, and AT&T. But when it comes to INWS, or this particular service, the National Weather Service will work with emergency managers to specifically define areas that they want alerts on. But if anybody on this call has gotten a wireless alert from the National Weather Service saying that there's severe weather going on in your area, that is the carrier's effort to better educate the public that dangerous weather is occurring. And you will get those alerts unless you opt out of those. But understand that there's a difference between the two that you are receiving. If anybody has questions about how these wireless alert works, please do contact me. My email address is about to come up as I'm concluding this presentation in the next couple of minutes. We're very active on Facebook. All National Weather Service offices have a Facebook and Twitter account, and you can receive your weather information that way. We get a lot of valuable information from social media. It's proven to be very helpful when disasters are occurring, especially when the cell phone towers go down. A lot of times, the internet will go down, so you have to have other ways of getting internet or getting onto social media. We want multiple ways of getting information to the public, and that's really important. The Storm Ready program is a special relationship between the National Weather Service and county emergency managers. This is Maryland. You see that much of Maryland is storm ready. A lot of the counties in Pennsylvania are also storm ready. To be certified as storm ready, you have to have relationships in place with your National Weather Service offices, multiple ways of receiving, disseminating, and transmitting severe weather information. And more, the Storm Ready program has been very successful in helping save lives and protect property. The Weather Ready Nation program is our effort to provide better, specific, site-based impact decision support information to private enterprise like hospitals, stadiums, parks, airports, schools, colleges, businesses, and even individual homes. We are trying to reach out to everybody to make sure they understand what a severe weather warning means, what the impact might be to them, and how they can best prepare to mitigate the effect of hazardous weather. We're calling it the Weather Ready Nation. So taking a quick look at the future of the Weather Ready Nation roadmap, we have a service plan in place out through 2020. We're going to provide this impact-based decision support. We're also doing this with climate information, hydro forecasting, aviation. Space weather has become very important. Solar flares, any disruption in communication that might occur from solar flares. We have a Space Weather Environment Center in Boulder, Colorado that issues space weather hazard information. If you haven't had the chance to look at that, it's actually kind of interesting. Just do a Google search on Space Weather Environment Center and you will find what you need out of Boulder, Colorado. We're deciding how to staff and how to train each of those 122 weather offices that you saw on the map that I provided a few slides earlier. We're looking at the science and technology aspect. After Hurricane Sandy, the National Weather Service was awarded with several $1 million to help upgrade their computer technology. Everybody's probably heard that the Europeans are ahead of the Americans in producing weather forecasts, that they're more accurate. We need to upgrade our computer system. We need to look more at ensemble or average forecasts. we've been given a healthy chunk of change to incorporate improvements into our computer models. You will start to see those as early as January 2014, and those will be widespread by March of 2014. You should see improvements in the American forecast models as we get into the spring and especially next summer. Step 4 of this Weather Ready Nation roadmap is the business plan. How is the Weather Service going to be economically responsible and viable, integrating into the weather enterprise, working with private industry to produce the best weather information possible? We have a plan in place. We're going to roll it out in the early part of 2014, and the National Weather Service will probably reorganize into big forecast offices in big metropolitan areas like Philadelphia and Washington, D.C., and then have smaller watch warning offices in places like State College and places like that. So there's big happenings in the National Weather Service as we talk right now because of the attention that's being paid to the budget side of the house. At this particular point, I will wrap it up. I will be happy to entertain any questions. There's my email address. Email me with any questions that you might have about anything that was said. I'm sure we can make this PowerPoint available to anybody who wants it, and I will, at this point, entertain any questions that anybody has.
Testing microphone. Can you hear me?
Yes.
Okay, hi. My name is James Hyde. I'm a geography major here at Mosville University as an undergrad. I'm planning to attend emergency management school sometime next year, going into graduate school. My question is that how do you merge risk-based forecast with impact-based forecast? You were talking about how in the lead up to events, I'm a native of Anne Arundel County, so I appreciate your forecast that you give me over at Sterling. So how do you merge those two forecasts? So we were talking about, I know you changed your, back in 2011 after Communigeddon, you changed your watch and warning policy so that those kind of impacts with commuting and other things would like, I guess, you change your policy so that when Communigeddon struck, after Communigeddon, then, I lost my train of thought. Sorry. How do you merge those risk and impact-based forecasts so that, is it risk first, then impact later? Because the impact forecasts are more deterministic-based, while risk forecasts are more probabilistic-based. So how do you merge those two?
Right. Right. One of the first things we started to do this winter is we came up with a new probability of exceedance forecast. In other words, we're taking a look at a bell curve and we're trying to let people know what those goalposts are as far as winter weather. In other words, we've got 2 models out of 15 that are showing that we're going to get a foot of snow even though our forecast is 2 inches. The emergency responder needs to know that that risk is there, and he needs to know, he or she needs to know what the confidence level of that risk is. So we started to incorporate uncertainty into our forecast this year. Communigeddon is an excellent example. We have some extreme events to go by. Communigeddon, the derecho that we had in June of 2012, we can use those as extreme events, and what everybody wants to know is, how is this particular event going to compare to that? In the event of Communigeddon, we had winter storm warnings out for 4 to 8 inches of snow, but there was this burst of thunder snow, thunderstorms, lightning, a band that set up right over D.C. at the worst possible time, and it caused, just incredible problems. In general, the Weather Service did a good job issuing a winter storm watch and then upgrading to a winter storm warning. But when we saw something really exceptional happening, something extremely out of the ordinary, how do we get that message out to emergency responders? I mean, the derecho is a good example. A lot of those derechos fall apart when they hit the mountains, but this particular one actually got stronger. So the National Weather Service did issue a statement saying, hey, this thing is holding together pretty well. But in our Twitter-based society, most people will only take a look at maybe the first 120 characters of a statement that the National Weather Service issues, which is why we wanted to develop the ability to ping everybody, hey, we've got something really special going on right now. We need to have a quick conference call in a half hour to talk about this. And just the fact that the National Weather Service is calling a conference call will alert emergency managers to the fact that there's something unusual happening. So that's in our hierarchy of support. The best thing that we can do is introduce the range of possibilities, which of course is going to be bigger the farther out an event is, and narrows the closer an event gets. But if the relationships are in place and the communication is good, if our forecast is out there and Weather Service says, hey, we need to have a talk now, there's something really special going on here, that alone will cause an emergency manager to go, well, I better listen to this and see what they're saying. And that'll give us the opportunity to respond accordingly. So we are issuing statistical forecasts and deterministic forecasts, but it's really difficult to quantify what's going on in the head of a meteorologist. That's what an emergency manager wants to know. Hey, do you think this could be another Communigeddon? Do you think this could be another derecho of 2012? Sometimes there's no better way to convey that information than having a conference call. But we're doing our best to introduce a range of possibilities in our forecast so people can take a look and see what the best case scenario is, what the worst case scenario is, and what level of acceptable risk they should plan for when they decide to call in for extra staffing, because we understand that costs money, you get overtime, you get resources. Once we mention some ice, VDOT will roll out like 600 snowplows across Northern Virginia, and that costs a lot of money. They don't want to do that if it's all going to be rain, but if there's a chance of even just a little bit of ice accumulating on the road, they're going to have to do that. So it's really interesting that an emergency manager needs different forecast information than the media or the general public. You have to consider the fact that it's the job of the emergency manager to protect people's lives and property. It's the job of the media to get a story. So in a lot of cases, we will communicate different information to an emergency manager than we will the media. Because if we tell the media that there could be a foot of snow in D.C., they'll go ahead and lead with that worst case scenario. But an emergency manager, we want to tell them, look, this isn't what we're forecasting, but there's a possibility that that front could slow down and this could turn out to be a worse situation than we're forecasting, and we want you guys to know that when you're making phone calls and spinning up your staffing. Does that make some sense? So a lot of what we're
that makes sense. And I have
Go ahead.
Go ahead.
Yeah, a lot of what we're gearing towards now is integration into the emergency manager's responsibilities. And that's where I think the future of the National Weather Service is going. And more we'll see private enterprise work with the media and the general public as far as what types of weather conditions to expect.
That's great. And I have a second question. So you talked about indices. So in terms of fire weather, there was the Hain index and things like that. For hurricanes, we have the Saffir-Simpson scale. We have the NESDIS scale for which Louis Cucciolini and for northeast snowstorms. What about other indices? Like there's a new indice for ice called the Sperry. It was Sperry something ice index from it was a guy developed by the MIC down in Tulsa with co-op partners. Like, do you think that we could use these indices and numerically based risk assessments to help convey information? So going back to like the Communigeddon days, 8 to 12 inches during the middle of the night is not a big deal. Right. That can be plowed away in terms of a day, but during a Communigeddon, that's a high impact event.
Right. Well, you bring up a couple of good points. First of all, the time that an event happens will have a huge impact on the result. If you have 8 to 12 inches of snow on a Sunday afternoon versus 8 to 12 inches of snow at 4 o'clock on a Monday morning. Secondly, there is definitely good information to be found from looking at statistically, from a standard deviation standpoint, how this particular weather incident stacks up to climatologically what's happened over the last 50 to 100 years. In other words, this particular surface low is X amount of millibars, and this is 2 standard deviations outside of the normal that we see in November. And those northerly winds are 3 standard deviations stronger than what we normally see this time of year, combined with moisture that is in the 90th percentile. And when you begin to see these extreme events way out towards the end of the bell curve, it gives us more confidence in forecasting an extreme event. The Storm Prediction Center in Norman, Oklahoma has started to use this in forecasting tornado outbreaks. They take a look at convective available potential energy. They take a look at the amount of juice that's in the atmosphere on this particular day versus what climatologically they've seen over the last 50 to 100 years. And if they see something that's way towards the end of that bell curve, they will issue something called a tornado emergency. We are looking for ways to let people know that we've got something special happening. I know that the Weather Channel has started naming winter storms. I know that there's been a lot of talk of categorizing winter storms and things like that. One possible danger is if you categorize a hurricane, say from Cat 1 to Cat 5, hurricanes are categorized by their wind speed and wind speed alone. A Cat 5 hurricane with 165 knots of wind is just categorized by wind. It's not categorized by the amount of coastal flooding that's expected, the amount of tornadoes that it might cause, the amount of inland flooding it might cause, the size of the storm, how fast or how slow it's moving. There's like 5 or 6 different threats in a hurricane. So there are limitations to categorizing weather events. When it comes to a hurricane, most people understand that a Cat 5 storm is stronger than a Cat 1 storm. But what most people don't understand is that a tropical storm, something that's not even a Cat 1 hurricane, can cause more problems for you than a Cat 5 hurricane, depending upon how much rain it may cause or how much inland flooding it could cause. So what we've decided to do is try to look at each of those individual threats, inland flooding, tornadoes, wind, coastal surge, categorize each and every one of those, and then issue warnings based upon those threats. Does that make some sense? So if a storm surge is going to be 10 to 12 feet, that's extreme. And a tropical storm could cause that if the winds are correlating with astronomical tides. Yeah. So there are risks in categorizing things, but where I think we're making some improvements, and we're actually going to start doing this next year, we're going to issue coastal flood warnings instead of necessarily hurricane warnings. Does that make some sense? Because a hurricane has like 5 or 6 hazards with it. And we're trying not to just generalize, this is a Cat 5 hurricane, but we're trying to say the threat from this tropical system is coastal flooding, and this looks really dangerous for coastal flooding.
Yeah, and it's like your examples, Ike in 2007 or 2008 was, Allison 2001 down in the
Allison
Houston
is a great example.
Weather aficionado on the side.
Absolutely.
Yeah, I'm kind
Allison
of a weather aficionado on the side. So
yeah, we caution people not to get caught up in this, well, it's just a tropical storm mentality. There is a real danger in doing that. And that's a limitation of the categorization scale that's been in effect for years. We recognize its limitations, but changing that is difficult. Getting something that everybody can agree to is difficult. The best that we can do is try to break down what those threats are and what the risks are of each particular threat for your individual area. Absolutely. So some excellent points.
All right, I'll rest my questions and comments for now for other people.
Okay, real good.
Terry, you have a question?
Yes, I'm in my senior year of meteorology here at Millersville, and I am asking you if you know whether or not the National Weather Service is going to come out of their higher freeze after they do that reorganization next year, and if not, how would we go about getting involved with incident meteorology with them?
Yeah, that's a real good question. And understand, for those of us that have been with the government for 20 plus years, the government tends to go through periods of expansion and contraction. Back in the 1980s, under the Reagan administration, the government contracted quite a bit. In the 1990s, it expanded quite a bit. We are going through a period of contraction right now, but we will go through a period of expansion again in the years ahead. In fact, the National Weather Service will decrease in size as the years go on, but what that will do is it will create, in my opinion, a real need for qualified people as the years proceed. In other words, if you can look out 5 years in the future, up to 30% of the National Weather Service is eligible to retire in the next 2 to 5 years. Once that happens, once the agency restructures, we're going to go through a period where we're going to have a real need for people that are qualified to do meteorology. So I would emphasize a real patience at a time like this. You know, federal employees are getting, it seems like, discouraging news day after day that we're downsizing, budget gridlock, and all of that stuff. Just keep in mind, administrations change, endeavors change. The weather enterprise, emergency response, is going to be one of the biggest growing fields in the next 5 to 10 years, and how weather is going to impact our society is only going to grow, especially if you get into water supply and climate and things like that. So while it may be bleak right now, if you just scooch out maybe 2, 3, 5 years in the future, I think you're going to go from a position where you can't find a darn thing in the National Weather Service to where you'll actually be able to pick or choose where you're going to want to be able to go. And the best thing that you can do as somebody in your position, go through the Incident Command System courses that FEMA offers online. Go to the Southern Region Headquarters, the National Weather Service Southern Region Headquarters Jetstream Meteorology course, and learn everything you can about, there's just so much online stuff. In fact, I would even just recommend at this point, just send me an email. The email is sitting up there right now. I'll give you about a half dozen links that you can go through online. And when are you graduating?
I'm going to be graduating in the spring, after spring.
The spring. Okay. Yeah, you're going to have a hard time getting in with the federal government right now. And it will probably stay that way through the remainder of the Obama administration. But I can assure you that if you go out maybe another 2, 3, 4 years beyond that, your skills are going to be highly needed by the federal government, because we're going to lose quite a bit of expertise and people that have been with the agency for many, many years, and we're going to need new people to come in and take their place. So the best advice I can give you is send me an email. I'll give you some online links to go through. I'll give you some people to contact, and I will tell you that you're in a field that is going to be very, very high demand in the next 5 to 10 years. Don't be too discouraged by what's happening right now. When it comes to the partnership between emergency management, the National Weather Service, and emergency responders, it is going to be really, really big in the future. As far as people that are, fatalities, natural disasters are becoming an increasing percentage of fatalities and impact on our national economy with each and every passing year. Climate change, water supply, all of that stuff. It's going to be huge as you get out to the later part of the 2010s and the next 10 to 20 years. And the National Weather Service recognizes that. Right now, sadly, in the federal government, we're going through this period where we just can't seem to get out of our own way. But the reality is that the need is just simply going to increase over the next 5 to 10 years. So I would highly recommend just be patient. Look at the private enterprise, look at broadcasting, look at private companies, and especially if you develop some expertise in forecasting, say 3, 4, 5, 7 days in the future, the National Weather Service is really concentrating heavily on the short-term stuff. We're going to need people that have ability to look at climate change, 6 to 10 day, month, 2 month, 3 month type forecasts. That need is just going to be immense as we focus more and more on the short term. So I would just have to say just hang in there. And the next thing you know, the National Weather Service is going to go through another modernization where we reallocate resources, offer up jobs, and hire people by the boatloads. It may be 2, 3, 4 years away, but it will definitely happen, I can assure you. I've been with this agency 20 years, and I've seen periods where people can pick or choose where they want to go, and I've seen periods where hiring freezes are in effect, like right now. This time period will pass, and a big hiring period is going to happen. It will go from a famine to feast mentality, but it's going to take a little bit of time, and I hope that makes some sense.
That does make perfect sense, but would you say, so you're saying maybe stay in school longer as much as you can and, defer off those loans and just wait for the hiring to come back? Or would you say that there are certain types of jobs that we could get now that would look good on a resume when you're applying for the National Weather Service?
Yeah, a lot of the National Weather Service offices have volunteer and internship programs where you can get some real-world experience. Broadcasting and news has it, and now more and more increasingly getting involved in emergency management, emergency responders, and the private industry. I'll give you an example. Out in California, there is a company called the California ISO. They regulate the flow of power from one part of their electrical grid to another during times of severe weather. And they are looking at bringing on private meteorologists to help them forecast specific temperatures, specific trends, climate forecasts, what have you. I think the private sector is going to be an area where there'll be a lot of growth in meteorology jobs, but from the government side, like you said, right now we're going through a hiring freeze. But you can always volunteer at your National Weather Service office, and they're going to restructure in 2014 and 2015, and I would say by the time you get out to like 2016, 2017, if you want to get in with the National Weather Service, there will be plenty of jobs available. And I would encourage you to contact me offline. I can talk to you more about this and give you some people to stay in touch with during this time.
Thank you very much. That was really helpful.
All right, any other questions for Steve? All right, I think this was an excellent presentation. It was by far one of the best received that we've had. Steve, I want to thank you very much for being participating today and giving us a great heads up, certainly giving some direction to our students. And if there's nothing else, I will say everybody have a good afternoon, a good weekend, and keep watching the weather.
Thank you.
Thanks again, Steve.
Bye.